Of the three states of matter, gases are the easiest to study, at least under normal temperatures and pressures. You don't worry about the intermolecular forces that much, and the particles are moving around and colliding. It's relatively simple to model them. Liquids are harder. They're in between the gases and the solids. Liquids and fluids are something that are studied especially in physics. In this chapter, we're going to look at solids. Solids have the advantage of regular patterns or arrays in almost all solids. There are some solids whose atoms or ions or particles, basically atoms, are not necessarily in predictable patterns or arrays or lattice structures. We'll get into that in a little bit. So talking about metals and metal-containing compounds, of course, a God of providence has given us a planet where in the crust of the earth, which is as far as we've gone so far, there are lots and lots of metals and metal-containing compounds. Of course, they're not evenly distributed throughout the planet. Some countries have more of one kind of element or compound than others do, and it's almost like it's God's intention that maybe countries learn how to get along with each other and trade and interact, which of course is absolutely true. Excuse me. Having a little bit of a morning cough here. In any case, let's talk a little bit about lithium. You've heard about lithium an awful lot in the last several years, having to do with batteries. And as we move to a more and more electric society, for example, electric cars and so forth, lithium is becoming increasingly important. And you can see in this picture that there are large deposits of lithium in places where water is able to evaporate rapidly, leaving behind the minerals that were dissolved in that water. And one of those places, as you can see, is a high plateau in Bolivia, South America. I've been within, several kilometers of the border of Bolivia when I was down in the Tambopata jungle region of eastern Peru. In any case, as the water evaporates, it leaves behind the minerals. We have all kinds of wonderful minerals that we use all the time. Of course, we talk about copper and aluminum. We talk about lead and iron, very, very common. But there are some more very important batteries as well, metals as well. Lithium, which is needed in a lot of these modern batteries, is an alkali metal, left side of the periodic table, pretty high up, very reactive. And a lot of our hybrid cars, as well as now the electric cars, such as Tesla, are going to have very fancy batteries. These cars are pretty heavy because of all the metal it takes to make the batteries. That means their tires wear out a little bit faster, the roads wear out a little bit faster. We're going to need more and more charging stations in order to support this industry. But we're also going to need an awful lot of lithium. And many of the world's largest supplies are in Chile and Bolivia in South America. You mine the lithium as a compound, lithium carbonate. Of course, you're not going to find lithium itself in its pure form in the Earth's environment because it chemically reacts with water to make compounds. Once we mine that lithium carbonate, we convert the lithium carbonate into lithium chloride, and then we can pass electricity through lithium chloride. We call that electrolyzing it in order to get the pure lithium. We'll talk about electrolysis in our electrochemical chapter coming up later in the book. Well, let's get into this discussion of solids. As usual, when we look at all the different kinds of solids in the planet and on the planet, once more, as is the case, we see in God's creation a tremendous diversity And in that diversity, there are similarities which allow us to categorize them. That is essential for the categorization of all kinds of things, from subatomic particles to solids to butterflies to stars. There's diversity and unity every place we look. It's a reflection of the Trinity. So in solids, the kind of motion, three motions that we talk about, the translational motion, the sideways motion, if you will, such as talking about up here, is pretty minimal because they're locked in this crystalline construction. There is a little bit of rotation, and of course there's going to be some vibration within these crystal structures. And when we look at all the different kinds of solids, we have these 5 categories over here. The ionic solids are going to involve, as you might well imagine, ions. They might be monatomic ions, they might be polyatomic ions, and of course the opposite charges attract each other. And you can see some of the properties of ionic solids. These attractions between oppositely charged particles are so strong that they have high melting points. They're poor in terms of their conductivity when they're a solid, but when they reach their melting point and the ions are now mobile, remember you need mobile charged particles in order to conduct an electrical current, they become good conductors, and you have high conductivity when you exceed their melting point. Then we have just pure metals. And pure metals, the ions, once again, the atoms, I should say, once again, are stacked in predictable patterns or arrays. Now, the reason they can hold together is because these electrons are delocalized. It's like you have a matrix of nuclei swimming in a sea of electrons. The word sea, S-E-A, is sometimes used in the literature in place of delocalized electrons. So in other words, instead of the electrons being relatively locked into their particular orbitals, they are very, very mobile, which is why metals are good conductors of both electricity and heat. Metals are malleable, which means it's easy to bend them, and they are ductile, which means it's easy to stretch them into long wires. And again, they're good conductors of electricity and heat. When we talk about molecular solids, obviously we're talking about molecules which are in their solid state, and of course that depends upon what the temperature is in order for them to be in their solid state. But you can have molecular solids, and what's going to hold them together are going to be your dispersion forces, otherwise known as the London forces. But also some of your molecules might be polar, so you can have your dipole-dipole forces. And on occasion, obviously, when you have nitrogen, oxygen, or fluorine involved, NOF, so to speak, then you're going to have your hydrogen bonding, which is going to hold these molecules together in their solids. And the hydrogen bonding, as you would expect, would have the highest melting and boiling points. But notice, of course, that these are very, very poor conductors of electricity. Right there. Number 4, we have our network solids. And these network solids can be in 3 dimensions, or they can be in 2 dimensions. Graphite has a tendency to be 2-dimensional, so you form sheets of carbon atoms, and they can slide over each other, so graphite is very slippery. But in 3 dimensions, you have diamond, so you go from one of the softest and slippier solids to one of the hardest materials that we know about, the diamond. And here the bonding is going to be all covalent. And you're going to have a very, very wide range of hardness and melting points depending upon their 2-dimensional or 3-dimensional arrays. Finally, you have the solids that don't form any regular pattern or geometrical lattice structure. And examples of this would be glass and some of the polymers that we can make. So you can see what the arrangement of some of these solids would look like in these pictures. From our polymers over here, to our ionic solids over here, to our metals over here, to our networks over here. But the amorphous solids don't have any regular repeating pattern. They are relatively rare naturally, but pretty common in terms of all the polymers that we make. So when we talk about these three-dimensional structures, we often use this word a lattice, which is like a geometrical array, a packing. And when we pack these solids together, it might be at the atomic level, the ionic level, or the molecular level. Those are the three particles we typically deal with when we talk about chemistry. And in a solid that is not amorphous, we usually are going to discover a unit cell. The unit cell would be the smallest repeating unit that has all of the symmetry characteristic of the way the atoms, ions, or molecules are arranged in the solids. I'm just reading from right there. In other words, when you get smaller than the unit cell, you lose the pattern and the repeating nature of the structure. And we have ways to discover what these unit cells look like, something called X-ray diffraction, which we'll get to in a minute. And again, we can categorize the unit cells. And we have various patterns that we see across the periodic table. One thing that we have to remember is that unit cells reflect the stoichiometry of the solid. So if you've got a compound that is made up of multiple different kinds of atoms, the unit cell will reflect proportionately what the number of the different atoms are in the formula of that solid. So for example, with sodium chloride, you would expect a unit cell to have a ratio of 1 sodium to 1 chloride. But in calcium chloride, you would expect a unit cell to be in the ratio of 1 calcium to 2 chlorides. We also talk about lattice points. Lattice points are the points of the unit cell. And we like those points often to be at the center of our atoms or our ions. Now, if you look at this picture at the bottom, you can see that in picture number 1, right below the number 1 that I just wrote, you can see that there is one small atom, and there is a fourth of an atom that's part of the one corner, a fourth of the atom part of another corner, another fourth in that corner, and another fourth in that corner. And so 4/4 gives me one big atom to go along with this middle atom, which is a small one. We could also draw the unit cell where we have the big atom at the center, and we have 1/4 of 4 different small atoms, and we still get a 1-to-1 stoichiometric ratio of atoms. Or we could get real creative right here. And now when you look it up, you can see we've got half of a small and half of a small, which gives me one whole small atom. And you can see we have 2 small parts and 2 larger parts of the big atoms, which again adds up to one entire big atom. You can also see that the different types of unit cells are going to depend upon whether all of your angles equal 90 degrees, like in a true cube, or 2 of the 3 atoms are 90 degrees, or only one of the 3, I shouldn't say atoms, I mean angles, one of the angles is 90 degrees. You can also have all 3 sides the same length. 2 sides can be the same length and one isn't, or all 3 sides can be different lengths. And all those variations, these parallel pipeheads, except for the hexagonal cellular arrangement, are variations of the different types of unit cells with their repeating structures that we find in solids. So this assemblage of three-dimensional unit cells is called a crystalline lattice structure, a repeating geometrical array. Now, you'll notice in the next sentence, beginning right here, to construct crystal lattices, nature can use any of 7 three-dimensional unit cells. So we have a fundamental categorization of 7 different categories of unit cells. But notice this phrase, nature can use. Well, nature is not a being. Nature does not have a mind, unless, of course, perhaps you're a pantheist. And what we're talking about here from a Christian perspective, obviously, is that God, in his creative genius, when he invented all of these things and created all of these things and gave them the properties that all of these things have, put them into what we see as 7 groups. Now, and we get those 7 groups by varying their relative lengths of the sides. They could all be the same, they might not. And by varying their angles. They could all be 90 degrees, they might not be. The simplest one is going to be the cubic unit cell, which would have all 90-degree angles and all sides of the same length. And we can divide the cubic unit cells into 3 subcategories. The primitive cubic cell, or simple cubic, the body-centered cubic cell, and then the face-centered cubic cell. Now, what do we mean by body-centered and face-centered? Well, in body-centered, down here, you can see that in the very center of the cube is one of the atoms. In the primitive or simple cubic, there is nothing inside the 8 corners of the cubic cell. In the face-centered, you have a cubic cell. In the front face, you have an atom, half of which will belong to this unit cell. The other half would belong to the unit cell that's adjacent to it. Then on the far side, way in the back, you've got that one. On the top, you've got this one. On the bottom, you've got this one. In the very back, you've got that one. And on this right side, you've got that one. And so if you look at these pictures down here, you can see how in all of these cases, you can calculate the ratio of the small atoms to the big atoms by adding up all the parts in the unit cell. Now, when you look at the periodic table to see if there's any pattern, there doesn't appear to be much of a pattern, at least as far as we can discern yet, in terms of maybe all of the body-centered are located together, and they do seem to be over here and here, but you've got an oddball one there. And when we look at the cubic close packing, the face-centered cubic, they seem to be pretty much all here, but there are a few in outlying places. And there only is one simple cube, and that's polonium. So there are some generalities, but nothing seems to be true across the board. So when we talk about the primitive cubic arrangement, it has one net atom within the unit cell. And depending on how you want to look at it, whether you draw your unit cell using corners, or there are different ways you can draw it, you end up having, in total, one entire atom in that unit cell. Now, we'll take a little diversion here since it's the next page. If you've ever been to the grocery store where they pack oranges or apples or grapefruits, and you can see that there's a packing arrangement that is more stable and takes up less space, so that when somebody reaches for an apple that they think is better than the apples around it. Hopefully the whole stack doesn't come falling down. What you ought to notice is you've got some space in between the apples or the oranges or the marbles or the balls. And depending on the packing, you can see that in this particular arrangement, there is less space between the atoms or oranges than there is on the left when you look at that red area that I colored in. So there are some ways of packing the atoms are more efficient than others. Here's an efficient way of laying marbles out on a table, and you get the hexagonal structure, and you've got the space between the marbles right in there. And this is called hexagonal close packed, HCP. They use the arrangements, the letters, to abbreviate it because they're so common. And then when you take the hexagons, or the cubes for that matter, you can see that once you create one layer, the next layer is going to have to be offset a little bit so that it can rest in the spaces and reduce the amount of space, thereby making the packing a little bit more efficient. And here's how we learn a little bit about the packing. And that is by, or the crystalline structure. And that is we take these high energy photons, and if they are high in energy, remember that the frequency is proportional to the energy. If you remember the equation, energy equals Planck's constant times frequency. So we have high energy X-rays, so they have high frequency. And if you remember this equation right here, the speed of an electromagnetic particle, not a particle, but photon, equals frequency times wavelength. If you have a big frequency, it means you have a very small wavelength. And the very small wavelength allows it to discriminate extremely small particles, like the particles that make up a solid. So that's why we're using X-rays and not some other part of the electromagnetic spectrum. And so we direct this beam at the sample, which is right there, and then the X-rays get scattered in predictable patterns because the particles in the sample are in predictable patterns or array, the lattice structure. And that pattern shows up then on this photographic film or these electronic detectors, and an X-ray crystallographer would be able to, from experience and training, say, well, this particular pattern that I see on the film represents a particular type of crystal lattice structure. Now, the last thing we have to do is go through the rather complicated math problem. Math problems having to do with crystal structures have a lot of parts often. In this particular problem, you're given 4 pieces of information. You're told that it's aluminum. You're told its density. You're told it's face-centered. You're not told its radius, but you're asked to find the radius. That's number 4. A math problem of this sort can give you any 3 of the 4, and you should be able to find the 4th one. So, we know that it's aluminum. We know its density. We know it's face-centered. And face-centered then would look like this if I draw one layer just on the front side of the cube. Obviously, there would be a similar type of arrangement on the other 5 sides of the 6 faces of the cube. You'll notice that my radius here the diagonal, this diagonal along here, is equal to 4 radii, a piece of information that will become important later in the problem. And you'll notice that we have an isosceles triangle, which means we're going to have a 1 square root of 2 ratio between the side, and the hypotenuse. That's also going to be important. So coming to the actual solution, the first thing we need to do is to calculate the mass of the unit cell. So we can begin by calculating the mass of an atom. And we know its molar mass from the periodic table for aluminum. and we know Avogadro's number. And so the first thing we find is the mass of one atom of aluminum. Then we can find the mass of the unit cell, because in a face-centered cube, you're going to have 4 atoms. So we're going to take this number, 4.480 times 10 to the minus 23 grams, and multiply it by 4, because it's in a face-centered cubic structure, you're going to have a total of 4 atoms. And this is the one of the most common mistakes made when students try to do problems like this. And that now gives me the mass of an entire unit cell with the 4 atoms in it. The next thing we're going to do is calculate the volume of that unit cell. So we take its mass in grams and we multiply by the density, but we're going to put the volume in the numerator and the mass in the denominator, the reciprocal of the density, so that mass cancels, and now I have the volume of my unit cell. Once I know the volume of my unit cell, I can find the length of a side, because if I have a cubic cell, you'll see over here in my drawing, the volume of my cubic cell is length cubed. So if I take the cubed root of that length, I get the cube root of that volume, I get the length of my unit cell, 4.049 times 10 to the minus 8 centimeters. Now, the next thing we're going to do is calculate the atomic radius. And again, if you remember the previous picture where I showed you that there are 4 radii along the diagonal, 4 radii. So, and then if we remember it's an isosceles triangle, you have an edge, and then you have the diagonal distance, which I've abbreviated DD. And so you're going to use the Pythagorean theorem. You're going to square this, square that, which gives you 2 times the edge squared. That could have been a little confusing when they put that 2 in there. And when we solve for take the square root of both sides. So you take the square root of that, take the square root of that, and now you get this equation right here. And so your diagonal distance is going to be the square root of 2 times the unit cell edge, which gives us this distance for the diagonal. And since the diagonal was 4 radii, we divide by 4, and now I have the actual radius of an aluminum atom. And as is common in solid state physics and chemistry, we often like to convert that into picometers, which is the trillionth of a meter, and we get this answer right here. And that, my friends, is about as hard as a math problem as you're going to see in talking about solids. We're going to stop right there.